So let's get started. So my goal today is to focus on chapter 33. Hopefully I can cover the whole chapter today. If I can cover the whole chapter today, then the lecture next week will only be about an hour and a half, and you'll probably be joined by my Monday-Wednesday group, because I have a scheduling conflict next Wednesday, and so I'm going to have them join us next week. It won't be a lot of students, but okay. So your chapter 33 homework is due on the 7th. Be due next Tuesday. And motor lab is due this week. I've only gotten a couple motor labs done, one from the Tuesday section, one from the Monday-Wednesday section, and then the transient lab too. So make sure you get those ready. Turn them in on Friday. Okay, Friday is, I'll talk about the last lab. We will have a meeting on December 10th, but that'll be for the exam. Okay. All right. So these are the topics I want to cover today, chapter 33. They build on materials in chapters 31 and 32. Okay? Just one second. So the goal of this chapter is to look at how resistors, capacitors, and inductors behave when you apply AC current. Now, I got to define what AC current is, and we're looking at a particular type of AC current in this chapter. Okay. AC current, as opposed to DC current, there's one slight difference. With DC current, the electrons move in one direction. The current doesn't have to be constant, but the current has to move in one direction. I can build a DC generator, and I talked about this last week or 2 weeks ago. And the DC generator produces an EMF that looks like this. Which is the absolute value of a sinusoidal function. Okay, the current always goes in one direction. The electric field that's induced is always in one direction. It just varies with time. But basically, this is the absolute value of the sine function or cosine function. Although what I drew here is the sine function. Okay? AC current, the electrons can move in either direction in the circuit. They can go back and forth, left or right. Okay? That's the main difference. So you can apply to a resistor a voltage that looks like this. And this will produce an alternating current. What we're going to be looking at in particular are alternating currents that have this functional form. We're going to look at alternating currents that have this functional form. They vary sinusoidally with time. These are produced with a generator. This is what comes out of your wall socket. Now, whether I use sine or cosine is really not that important. It just depends on what my initial conditions are. However, the convention is to write my voltage in terms of the cosine function. Most of the engineering books write the voltage as a cosine function. Our textbook does not. It doesn't conform to a standard. Okay, but I'm going to write everything in terms of the cosine function. It's because everybody else does it except for our textbook. Now, what is omega? Omega is 2 pi times the frequency. And in your house, F is 60 hertz. and omega, then it turns out to be, if you take 60 times 2 pi, is about 377 hertz. Okay, so it varies. You go through 60 cycles per second. So if you were able to take an oscilloscope and stick it into your wall socket, you would see a sinusoidally varying function. This value is not what you think it is. You might think it's 120 volts. Actually, it's about 170 volts. And we're going to talk about where the 120 comes from. Okay, we'll talk about where the 120 comes from today. And so really what comes out of your wall socket is something that looks like this. And so sinusoidally varying power supplies have a lot of applications in real life. So that's why we want to focus on this type of power supply. So we're going to drive a circuit with this type of power supply. Square wave functions are a little bit more complicated to analyze. We won't do them here. We're only going to look at this type. And like I said, they have a lot of practical applications. And that's why the focus is on this. Generally, when you have any power supply with resistors, capacitors, and inductors in your circuit, what you end up doing is you end up solving a second order differential equation by applying Kirchhoff's laws. We're going to come up with a lot of different examples in this chapter. We're going to encounter a lot of different examples in this chapter where we have to apply Kirchhoff's laws. But what I'm going to do is I'm not going to solve a differential equation every time I come up with a problem. I'm going to introduce to you a topic that will allow us to analyze circuits that are driven by these kind of power supplies without having us solve a second order differential equation. And that topic is called phasors, and I'll talk about that in a little bit. So the primary goal of our chapter then is, given an AC voltage, a sinusoidally varying voltage in a particular frequency, and various elements in your circuit like resistors, capacitors, and inductors, find the current in the circuit. And what will be particularly interesting is we're mainly going to be trying to figure out what is the amplitude. Okay, we're not really interested in this part. This is the phase part, how it varies with time. We're more interested really in the amplitude. You'll see most of the problems, and most of the problems we're just focusing on the amplitudes. You'll see that in the homework. So I want to say a few things about standard notation regarding the way our textbook does it, and I'm going to follow that, is whether I write voltage or current, if I'm going to write an instantaneous value, in other words, V is a function of time, I'm going to use little v. Peak values, I'm going to use capital letters with a subscript m for maximum, or the amplitudes. RMS values, I'll put capital letter with the RMS, and you'll see what RMS means in a little bit. Okay. So I just want to mention that when you have a sinusoidally varying power supply, this term is called the amplitude, the maximum value. Okay, so I'm going to refer to that, and this term V sub m is the maximum value of that function. It's the amplitude. Okay, it's the peak value. Okay, so this is the peak value. The distance from peak to trough is called the peak-to-peak value. You'll hear those terms sometimes. So how does this apply? How does this work with a circuit that just have a resistor? Does Ohm's law still apply? So if I have a circuit with a power supply that varies sinusoidally with time, How do I write the current? Well, the current is going to be V over R. And that's it. So Ohm's law still applies for an AC circuit. Okay. V and I will change with time, but their instantaneous values will follow Ohm's law. In addition, the two functions are in phase, meaning the peaks occur at the same time, the troughs occur at the same time, the zero occurs at the same time. So these two functions that represent voltage and current are completely in phase when you just have a circuit with a resistor. And so you see in the slide a picture of V as a function of time and I as a function of time. They're in phase. Okay. And again, I sub m here, I should point out that I sub m in this particular case is V sub m over the resistance. It's a voltage over something in ohms. Suppose I were to use a multimeter to either measure current or voltage. What does it measure when you're measuring AC current? So in a multimeter, you'll have a setting for AC. It'll be a button you'll press for AC. Okay, if you're measuring AC current or AC voltage, you got to make sure that your meter is in AC mode, because otherwise it'll always read zero, because the meter will just try to measure DC. Okay. When you do your last lab this semester, you're going to be measuring AC currents and voltages. You got to make sure that you have the meter set so that it's set to measure AC. Okay. But what did I tell you? Because if you're measuring something that varies or goes through a cycle 60 times a second, what is the display going to be on the multimeter? Because you can't see something change 60 times a second. Okay. Actually, it's actually the amplitude, the absolute value of the amplitude actually occurs every 120th of a second. Well, let's take a look at the power dissipated in that circuit. I'll give you an idea of what the multimeter is actually measuring, or what the multimeter should be measuring. Okay. So what is the power dissipated by this resistor? Well, it's I squared R. But what's I? Sorry. What's the power dissipated by the resistor? Because what the meter is going to be measuring is something related to the power. But it's not the instantaneous power. Okay. You're going to see a number displayed on the screen for I. What is that I? Well, it's reflected of the average power over a cycle. So this I is I effective. So let's take a look at the average value of the current over a cycle. Okay, I want to look at the average power over a cycle. Then we can look at the average current over a cycle, etc. Not the average current over a cycle, the average of the current squared over a cycle. Okay. So I want to look at P average. The multimeter is going to show you the square root of this value. Okay, the r's cancel. So I squared effective is I sub m cosine omega t squared average. So all I got to do is figure out what is the average of this function. And then I can figure out what I effective is. Okay? I want to find the average of the cosine function. How do I find the average of a function using calculus? Well, I think in Cal 2 you'll learn this, that the average of some kind of function f sub t is 1 over the interval times the integral of that function over the interval. Well, in our particular case, we want the average of cosine squared and I'm going to try to do this without doing an integral. Okay, I'm going to try to do this without evaluating the integral. By looking at the function for cosine and looking at the average, looking at cosine and looking at the function cosine squared. Let me ask you guys something. What is the average of the cosine function over a cycle?
Is it 0?
It's 0, right? We know. Okay. So we know. And that's the same is true for sine, right?
Yeah.
We know that's true. But what is this? And the trick to this is to realize that cosine squared omega t can be written using a trig identity in the following manner. Cosine squared omega t, I don't have to put it, just in general, is 1/2 of 1 plus cosine of 2 times omega t. Well, if we know this is the average of this is 0, what's the average of this one?
Wouldn't that still be 0?
Yeah, so the average is 0. So the average of this guy is 0. So isn't it true then the average of this function is just 1/2? But if I take the average of this will be 0. I'm left with 1/2. The average of a constant is the constant. Okay, so then this whole thing is 1/2. And so what I'm left with then is I squared effective is 1/2 I sub m squared. And so I effective is 1 over the square root of 2 I sub m. And so what your meter is measuring is the square root of the square of the average of, let me rephrase that. It's measuring the square root of the average of the square of the function. That's called a root mean square. And so we call this IRMS. And so your multimeter is measuring an RMS value. It's measuring 1 over the square root of 2 of the maximum value of the amplitude. That's what the multimeter is measuring. It's based on the average power in the cycle. So the square root of the average squared value. So IRMS is Imax times the square root of the average of the cosine squared function, which is a half. Well, what about VRMS? What do you think VRMS is going to be? Because I can do the same argument, right? And I can write this as V squared over R and do the same thing. So if IRMS is 1 over the square root of 2 Imax, what do you think VRMS is going to be? It's got to be the same thing, because the voltage is V sub m cosine omega t. I is I max cosine omega t. So they have the same functional form. They've got to be 1 over the square root of 2 times V max. So what's coming out of your wall socket? So at home, VRMS is 120 volts. Take your multimeter and you stick it in the wall socket, it'll tell you it's 120 volts. And notice that this VRMS value is independent of the frequency. See, in the US, the frequency is 60 hertz. In Europe, it's 50 hertz. But the RMS value is independent of the frequency. Now, granted, the voltages that are used in Europe are a little bit different. Okay? Their RMS voltage is around twice that value.
Professor?
Yeah.
So I actually work at a hardware store, and sometimes it says on like the outlets or whatever, 130 volts. Does that change anything?
130. I wonder where the 130 came from.
Yeah, I've seen 120 and 130. I mean, 120 is more common, but
I mean, I've seen 110 also.
Yeah.
Yeah, generally,
and then 220
I mean,
is the larger ones too, but yeah.
I think what's coming into your house is about 168 to 170 sine of omega t, or cosine of omega t. I don't know if that's a maximum RMS value. That's what's possible.
Okay.
And I think that the value, this number varies between 110 and 130. That's my guess. And this is somewhere in between.
That makes sense. All right.
Yeah, but that's a good question. Because I've seen them also. I've also seen 110 also. Okay. If you take a look at the power that's transmitted to your house, we use AC. We don't use DC. There's a reason for that. There's an important reason for that, because you're transmitting the energy over long wires. Those wires have resistance. And so the resistors, or the wires, will produce a power loss of I squared R. Okay? That's your power loss because the wires have resistance. So if you're sending DC current to your house, the power loss in transmitting the energy is I squared R, whatever R is. For the same value of I, if you use AC current, the power loss on average is 1/2 that. Because the average, when you look at this function, the average of cosine squared is 1/2. So you lose half the energy in transmitting energy to your home with AC as opposed to DC. It's one of the reasons why we use AC. There's a great video I have in your lab on AC current. You might want to take a look at it as to why we use AC over DC. Edison and Tesla were arguing about which, I don't remember, I think it was Edison and Tesla. They're trying to compete against each other as to what kind of energy should be delivered into the homes. You should take a look at that video. Okay.
Is that also why the band is named AC/DC?
That one I don't know. Just so we get a good understanding of how to calculate RMS values, I want to do one example for calculating an RMS value. Instead of having a sine function, I have a V varying as a triangle function. Okay, so remember that for AC, the RMS values, this is only for AC, I mean, this is only for sinusoidal. And then also P average is 1/2 I max squared times R. Let's look at a case where we have a triangle. We have some kind of generator that produces a triangle function. Now, how do you produce a triangle function? Well, it turns out you have to use a series of sinusoidally varying functions to produce a triangle function. The more sinusoidal varying terms you add, the more triangular it'll get. Of course, there's got to be some factor in front of the sine functions. So let's assume we have v as a function of time. Looks like this. So this is the period. This is V max. I want to know what is VRMS for this function. And so my goal then, I need to figure out VRMS is the square root of V squared average. So the first thing I got to do is write down what is V as a function of time. Okay, how do I write this as a function of time? Just over one cycle. Well, just the slope times the elapsed time. My slope is the maximum value over the period. And then t is the elapsed time. So this is my equation of that line. I just need to find the equation of this line. So it's basically the slope times the time, because my unwinder is set to 0. So V squared is V sub m over the period times the time, the whole thing squared. And now I want to find the average of this function over a cycle. It's going to be 1 over the period times the integral over the cycle of this guy. That's not a hard integral, right? I mean, oops. What's the integral of t squared?
T cubed over 3.
Okay, so I get t cubed over 3. And so I'm going to get v sub m squared over 3. And so now VRMS, I got to take the square root of this thing. Now when you look at this is smaller than VRMS. And so certainly IRMS is going to be 1 over the square root of 3 I sub m. So if this is smaller, then if I look at the average power over a cycle, then P average would end up being 1 over 3 I max squared R. So this, I'm losing more energy with this guy than with AC current. Why don't I use that to deliver energy to the house? Well, it's because of what I said before. I said that in order for you to produce this, you need a series of sinusoidally varying functions. And the frequency is going to be a multiple of 60 hertz, for example. So you're going to have, for example, A1 sine of 377t plus A2 sine of, what's 377 times 2? And I might not have this correct, but
754.
754. Depending on the function, you might only have odd multiples of this value or all multiples of this value in your series. And yet you can do a calculation to figure what that is. Okay, but anyway, it's a long series of terms. And so this is going to be hard to generate. Okay, especially if you're going to deliver a lot of energy. That's why we use the triangle function. By rotating a coil of wire in a magnetic field, it naturally gives you a sinusoidally varying function, and so that's why we use that. So going back again as a reminder, your room, your standard outlet. Of course, you have other outlets in your home, like the power, the air conditioning, and the refrigerator, the microwave, and your oven. Your standard. Actually, your microwave ones that run 20. Sorry, forgot about that. Your standard room outlet is 120 volts, approximately. It really depends on how consistent that voltage is the energy is being delivered to your house. It can go between between 110 and 130, I guess. That's why you see the 130 in some of those outlets. The maximum value is 170, and it runs at 60 hertz. In Europe, it's if I remember correctly, it's 240 and 50 hertz. But the frequency doesn't affect the RMS value. So we're going to look at circuits that contain capacitors and inductors and resistors. And like I said before, I can apply Kirchhoff's voltage law, solve a differential equation, and look at the outcomes. But first of all, we haven't had Math 33 in this course. In this course, you guys done Math 33 is not a prereq, and so I want to show you a different way that we can study circuits involving alternating currents. In fact, in particular, sinusoidally varying currents. And we're going to do it with something called a Phasor diagram. So we're going to analyze our circuits with Phasor diagrams. They're based on an idea called phasors, the general idea of phasors, which I'm not going to get into, but if you take Engineering 17 next semester, you'll learn about them. So what is a phasor? A phasor is a vector that's placed in a standard XY coordinate system. And in reality, what you learn in Engineering 17, the y-axis represents the imaginary numbers and the x-axis represents the real numbers. But we're not going to look at it that way. Okay? The phasor is used to represent a physical property that changes sinusoidally with time. This method will not work with signals that do not vary sinusoidally with time, like the triangle function. So this is going to be a mathematical construction that's going to help us to analyze circuits where the power supply varies sinusoidally with time. The length of the vector represents the maximum value of the property. So let me draw a picture. A phasor is just a vector. This is a special vector because it rotates in time. And we're only going to look at it at an instant in time. So I draw my XY coordinate system. And I'm going to draw my phasor. It has nothing to do with Star Trek. Okay, and this could represent voltage or current. Okay. The length of this thing is the maximum value. So if I were to write V as V max cosine omega t, this length would be this guy. Okay, and this vector rotates at the rate, well, at the frequency f. So if this were to represent what's coming out of the wall socket, the period of this vector rotating would be 1/60th of a second. It would rotate 60 times a second. The projection of this vector onto the x-axis gives you the value at any instant in time. And think about it, cosine omega t. All right, the length, this is the actual value at the instant in time. So when this is vertical, the voltage is 0. When it's horizontal, V equals V max. Oh yeah, and it rotates, and I got to remember it rotates counterclockwise. Okay. So the instantaneous value of the property is the projection onto the x-axis. And we can draw more than one phasor in this coordinate system, and I will add them like vectors. So if I were to add voltages, they would add like vectors. If I would add currents, they would add like vectors. That is the strength of drawing this diagram. Now, This diagram will work very nicely when we're looking at things hooked up in series or hooked up in parallel. But when you start getting into combinations of series and parallel, the diagram gets a little bit cumbersome. But you will learn a more efficient way to analyze circuits when you take Engineering 17. We just don't have time to do the more efficient way. Okay, otherwise I would cover it. So the diagram that consists of all the voltages and currents you put in your coordinate system, that's called a Phasor diagram. And so you got to be able to draw this picture. On the exam, you have to know how to draw a Phasor diagram. So phasors are really used to help to visualize what's happening in an AC circuit. Phasors are not physical quantities. They're just a way to help us to visualize and study AC circuits. However, it's not just for AC circuits, for anything that varies sinusoidally with time. So if you take 215 with me next semester, I'm going to introduce the concept of phasors again, but I'm going to talk about it within the context of light, where you have an electromagnetic field that varies sinusoidally with time. So let me show you an example of the phasors with the resistor and power supply in the circuit. Let me make this figure bigger for you guys. So in the graph, I show you V and I as a function of time. And on the right, you see the Phasor diagram for V and I. The red is V, the blue is I. And omega t is the angle at which we're looking at. It also shows you the projection onto the x-axis, the instantaneous values of V and I. They're in phase. So you draw them on top of each other. You draw the phasors on top of each other for the voltage and the current through the resistor. Okay? So that's the idea. And so we're going to use the phasors to solve circuits. We're going to use them to solve circuits that involve two elements in them, like a resistor and a capacitor, an inductor and a capacitor, inductor, capacitor, and resistor. So we're going to use the Phasor diagram to analyze the circuits as opposed to solving a second-order differential equation. Although on Friday, I will solve a second-order differential equation for the RLC circuit, where the power supply is varies sinusoidally in time. I think the other day I did it for a battery. This time I'm going to do it for a power supply that varies sinusoidally with time. Okay, so let's start analyzing circuits. And we'll start with just an inductor, a pure inductor, an ideal inductor. It has no resistance. We connect it to a power supply. This is very idealized because really inductors have resistance. We're going to pretend the resistance is negligible. Well, if I apply Kirchhoff's laws here, what do I get? Well, I get the power supply voltage is equal to the voltage drop across the inductor. How do I solve for I as a function of time? And it should be a small I, sorry. Let me move the dt over. Divide both sides by L. And if I want to find I as a function of time, I have to integrate both sides. And my constant of integration, I can arbitrarily set them to 0. They're actually irrelevant for the problem, so I just set them to 0. And so when I solve this, when I integrate, I'm going to get an omega out of it. And so this is my current in the circuit. It's 90 degrees out of phase with the voltage. Now what is this term? Omega times L. What units must it have?
Why is omega on the bottom?
Well, when I integrate this, don't I get a 1 over omega out of that?
Oh, I don't.
Right? If I integrate with respect to time.
Oh, okay. Yeah.
Because omega is just a number. And omega times
Because
L has
I was thinking
units.
of derivative.
I'm sorry?
Oh, I was thinking of derivative.
Oh, okay. Now omega times L has to have units of ohms, right? An amp is, right? Current is voltage per over resistance, right? So this has to have units of ohms. And it makes sense because, you know, L is a henry, it's an ohm second. An ohm second times 1 over second is an ohm. So omega times L has units of ohms. In fact, we're going to call it X sub L. We're going to define X sub L as omega times L, and we're going to call it the inductive reactance. So omega times L is the inductive reactance. It's a measure of the opposition to a changing current. Okay. I can also write this as V sub m over omega L times the cosine of omega t minus pi over 2. So V is V sub m cosine omega t. I is V sub m over X sub L. What this says is that the current is behind the voltage by pi over 2. By 90 degrees. Well, that should make sense because V is L di dt, so it's got to be a 90 degree phase shift between the two. What does this mean? It means that when the peak occurs, this guy's 0. So when V sub L is a maximum, I is 0. They're off by 90 degrees. The two functions are off by 90 degrees. Okay. And so there's a phase shift of pi over 2. In general, we can write V sub m, or I, is I max cosine omega t minus phi, where phi is the phase shift. When we look at circuits, this is what I will look like. It'll have this mathematical form where phi is the phase shift. In this particular case, phi is pi over 2. In the case of the capacitor, we will find out that the phase shift is minus pi over 2. So here's a phasor diagram for the inductor. It's actually kind of boring if you're just doing the inductor by itself. I show you the voltage across the inductor and the current through the inductor that's 90 degrees behind the voltage. I show you everything at some time omega, at some angle omega t. And you see that the peaks, when V is at a peak, I is 0. So the current lags the voltage by 90 degrees. Though that's something you have to memorize. The current lags the voltage by 90 degrees. Of course, you can do that. You can easily show that with the phasor diagram. So V equals V max when di dt is a maximum. And V equals 0 when di dt is 0. Okay. So, like I said before, omega times L, we're going to call the inductive reactance. It's omega times L. And it's a measure of the opposition to a changing current. Now, why does X sub L increase with increasing omega? Why does X sub L increase with increasing omega? That's because the induced EMF depends on the time rate of change of the magnetic flux. The faster this changes, the steeper the slope, the bigger the induced EMF. Well, if you have something as with this function, or something that has this functional form, the bigger omega is, the faster this function changes. And so the bigger your induced EMF. Oops. 1 second. Okay, so now I want to apply what we've learned so far about phasors. I'm going to do a circuit that has a resistor and an inductor. If I were to set up Kirchhoff's laws, I would get the following equation. Let's say this is our power supply voltage. I get the following equation. And I would have to solve that. Okay. I'm not going to use the methods of Math 33 to solve that. I'm actually going to show you how I can get all the answers I need by drawing the phasor diagram. I know that the voltage across the resistor is in phase with the current through the resistor. I know that the voltage across the inductor is 90 degrees out of phase with the current through the inductor. I also know that since these two are in series, they both have to have the same current through them. So let me draw a Phasor diagram. And, you know, I can draw the vectors, I can draw the phases at any angles I want. I can draw my first one at any angle I want, but I want to make life easy for myself. I want to start with something on a horizontal axis. And so, since they both have the same current through them, I'm going to draw the current, the phasor representing the current, when it's horizontal. You see why I chose this case. You can do the vertical one too, but that's okay. I mean, anything along the axis makes life easier for you, okay? So I'm going to draw that. And so what we said earlier is that the voltage across the resistor is in phase with this. So I'm going to draw the voltage across the resistor. Because remember, the current through both of these is the same. So what about the inductor? I'm going to choose a bad color. Sorry. What do we say about the inductor? The voltage across the inductor is 90 degrees ahead of the current. So I'm going to draw something 90 degrees ahead of the current. The length of it doesn't matter. Can you see that V sub L?
Barely.
Barely, okay.
I mean, I can see it just doesn't look green. It just looks kind of
it's kind of faint
blue. Yeah.
Okay, so I'm going to find the magnitude of that this vector. I'm going to add these two vectors together. Let me slide it over here. Because what I want to do is add this to this. Because remember, I said I can add the vectors together. And then the resultant vector is the power supply voltage. Right? Because isn't it true that this voltage, at any instant, this voltage plus this voltage has to be equal to that at any instant in time. But yeah. the phases are different, so I just can't add numbers. I can't say, if this was 30 volts and this is 40 volts, their maximum value, I can't say 30 plus 40 is 70. I can't do that because they're 90 degrees out of phase with each other. The voltage is going to be 30 squared plus 40 squared square root. Does that make sense?
Yeah.
Because this will have a cosine term, that's going to have a sine term, or vice versa. So I just can't add them numerically. So this triangle now that I've drawn tells you everything you need to know. Here, watch this now. I'm going to use the Pythagorean Theorem. Remember, V sub x max is really V max, okay? So I use them interchangeably. So isn't it true then that V sub m is a square root of V sub r squared plus V sub l squared? That's just geometry, right? And isn't it true that since they both have the same current, then I max times r squared plus I max times x sub l squared is V sub n, the maximum of the power supply voltage. Well, the I is common to both. And then I can solve for I. And notice I'm only interested in the maximum values. What about the RMS value? Well, the RMS value is going to be these guys divided by the square root of 2. Okay? If I divide this whole thing by the square root of 2, I get the RMS value, so big deal. So I'm generally interested in just the maximum value. I know they're going to vary sinusoidally with time, and there's going to be a phase shift. Their peaks are not going to occur at the same time. The peak of this one and the peak of this one are 90 degrees apart. But then there's a phase shift between the peak of the voltage across the resistor and the peak of the voltage across the inductor. I'm sorry, the power supply. We'll call it phi. Phi is the phase shift. And I get that from trigonometry because I can tell tangent of phi, opposite over adjacent, is that. So I can write it multiple ways. If I have this, once I have this triangle, I can figure out everything. Now, what's the voltage across the inductor? It's going to be the current times X sub L. Remember that X sub L is omega times L. The voltage across the resistor, again, these are maximum values. And again, X sub L is omega times L. What else can I get? Oh, I mean, I could do some trig. Cosine of phi is going to be V sub r over the square root of V sub L squared plus V sub r squared, which is the same thing as r over the square root. Let me erase some of this stuff. And we can do this for sine of phi. I pretty much have everything I need to know about this circuit by drawing the Phasor diagram. I can derive everything. So what I've done in the notes, I've constructed the Phasor diagram for you and shown you how I can derive everything from it. Oops. Just 1 second. Everything you saw on the screen is on that slide. In addition, I actually wrote V sub s as a function of time. please study that slide. And please rederive all those equations in that slide. Now, the one thing I did is I drew the phasor diagram in arbitrary angles, which really doesn't help if you're trying to derive everything from scratch. What you want to do, if you want to derive everything from scratch, you want to draw the phasor diagram as I did on the board with one of the vectors horizontally. It's hard to draw everything at an angle. I mean, you might be good at doing that. I'm not. I drew it when omega t minus phi was equal to 0. I'm sorry, I drew it when omega t was 0. Okay. Questions? Notice that phi is measured with respect to the power supply voltage. We're always referencing phi with respect to the power supply voltage. And so you notice that the current lags behind the power supply voltage by the angle phi. Let's take a look at the equations for the voltage across the inductor and the voltage across the resistor. Okay. Now, in the slide, you see V as a function of time. V sub r is a function of time. V sub L is a function of time. I'm interested in the amplitudes. And let me rewrite them by putting in the omegas in. What happens as omega goes to infinity?
Doesn't it go to 0?
This one goes to 0. What about this one?
That one, well, the omega would cancel. That's, no.
V sub L approaches this value. You have to use L'Hopital's rule because you get an infinity over infinity.
Yeah. Okay.
Yeah. So this ratio approaches. I mean, this thing approaches V sub m as. So all the voltage will be across the inductor as omega goes to infinity. So very high frequencies, all the voltage is across this. At very low frequencies, all the voltage is across this. Because at low frequencies, the inductor acts like a wire. So the resistance then we can say passes low frequencies. So if you make a circuit that looks like this, and let's say you hook up some load here. At high frequencies, all the current's going to go through the load. This is called a high-pass filter. You will see references to high-pass filters and low-pass filters in the book and in your homework. All they mean, high-pass just means the circuit allows high frequencies to go through. The voltage is maximized across that. So this is a high-pass filter because the voltage is across the inductor is maximized at high frequencies. So if I swap these two, then this is called a low-pass filter. Okay? So there's applications of filter circuits, although we use capacitors instead of inductors in filter circuits because inductors have issues one has to deal with, especially at high frequencies. I don't want to get into them here, but... Okay, let's take a look at a capacitor. Let's just look at a purely capacitive circuit, no resistors. And I won't need a phasor diagram here. Okay, so just a capacitor. Of course, the voltage across the capacitor has to be equal to the power supply voltage. The charge on the capacitor is C times V sub C. My current is just di dt. Excuse me. dq dt. Excuse me. So that's my current. Now omega times C has units, or must have units, of 1 over ohms. So I'm going to define x sub c as 1 over omega c, and that's going to have units of ohms. And we're going to call this the capacitive reactance. So we have X sub L as the inductive reactance. X sub C is called the capacitive reactance. R is the resistance. They all have units of ohms. And one thing I forgot to mention, combinations of these is called the impedance. So when I did the RL circuit, and I got this value, this is called the impedance. And I'm going to generalize it even more when I do a circuit that includes the capacitor and the inductor. Anything that combines the resistance and a reactance is called an impedance.
Are they all in ohms, or wouldn't X
They
sub
all
C,
in ohms.
isn't X sub C technically 1 over ohms?
No, omega C is 1 over ohms, but
Oh,
X sub C is ohms. That's why he wrote it that way. We're trying to make everything so it looks like Ohm's law. Right? I have a voltage over a resistance, right? That's what it looks like, doesn't it?
Yeah. that makes more sense. I think I wrote it wrong. So.
Okay. Now, we can also write this in the following way. And so this makes the phase shift, and so the current leads the voltage by 90 degrees, or by pi over 2. Okay?
What happened to the negative?
Because what happened to the negative? Good question. Isn't it true that cosine of theta plus pi over 2 is minus the sine of theta?
That's one of the identities, right?
Yeah, yeah.
Okay, all right.
Okay. And so this is the Phasor diagram for the capacitor. You notice that the current leads the voltage in this case by 90 degrees. Whereas for the inductor, the current lags the voltage by 90 degrees. So the voltage across the capacitor and the voltage across the inductor are 180 degrees apart if they were in the same circuit and in series. So one of the things you should try to do for practice is draw the Phasor diagram for an RC circuit. So I've done the RL circuit. I will do the RLC circuit. You should be able to do the RC circuit. And it should be easy because when I do the RLC circuit, you can just shrink the C part to 0. Okay, I'm going to go through this part real quick because I already talked about it. Notice that as for the capacitive reactance, as omega approaches 0, omega approaches 0 when, as omega approaches 0, I approaches 0. That means the capacitor acts like an open circuit. Okay, so let me check on the time. It's 12:20. This might be a good place to stop and take a break. I'll come back in 20 minutes. Okay? And then I'll discuss the RLC. This is the most important circuit in the chapter. So it will include everything I've discussed so far. So I think it's a good break. And they have a lot to say about this. This is going to be your lab. Okay? In your lab, you're going to be analyzing this circuit. So let's meet at about 12:40 to 12:45, okay?
Okay.
All right, so let me pause here.